Welcome back to Pentagram everybody. This will not be my most polished episode. I wish I could tell you otherwise. I told myself a while ago that if I was doing a channel update, then I probably made a mistake. There's not much of a script here. I mean, I had one, but it was for a previously an episode that was in production, but wasn't able to get it running. Issues with the video editor. So this one's going to be pretty much shoot from the hip using PDF document that I created. But before we get too far into the lesson, I want to say that this is probably going to be my last upload, possibly for years. There's just I'm putting way too much time and energy into this project. I was going to say for the relative gains, but it wasn't even that. There were I don't feel qualified to do this anymore. I guess it was a mistake getting started. I want to go back and retake some classes, and I decided last night. Right now it's about 7 a.m. on Thursday, September 30th, 2020. Excuse me, 2021. Yes, Thursday, September 30th, 2021, and it's about 7 a.m. Anyway, yeah, I decided last night I want to shut the podcast down, probably indefinitely. I've got some problems that I could put up on the podcast that are, I'm confident that they've got right answers because I did have them corrected in a class that I took. But unless I've got a second set of eyes here indefinitely, I think it's going to be a problem. And there's a lot of other classes I want to go back and redo. So sorry about that. Didn't have much of a title page for this one. This episode is going to be about the Laurent series for the function 1 over e to the z minus 1. And going to be, this is going to be an awkward episode, sorry. Not much of a title page here. The problem listed in the text, which I'll link in this, which I'll write about in the description, it did not list a domain for the problem. It was just they wanted a Laurent series about the origin, z equal to 0. So I wanted to, and when I was researching this problem, I looked, most of the answers I saw on the internet were from on the domain from 0 to pi, non-inclusive. So not including 0, 0 to 2 pi, not including 0 or 2 pi. And admittedly, I did end up going on the internet. That's another problem here. I shouldn't have been going on the internet. I should have known this problem before I began production. But I wanted to put up something interesting, so here we are. Anyways, I wasn't going to post anything at all. I was just going to leave the channel update that I recently put up and not say anything else, and just go about my business. However, I did find something in the day or two after I posted that channel update that made me decide this one episode might be worth it and might actually make a fitting way to go out, so to speak. I'll still be here. I'm not going to be posting anymore. I guess I'll just try to jump in the way I originally planned to start. In the hint of this problem, they did list a hint saying that the function 1 over e to the z minus 1 has a simple pole. The first thing I found myself asking is, what is a simple pole? And this is a pole about the origin at x and y. This is a function showing the absolute value of the function f of z, and the absolute value being a real number. So this does not apply to an actual, representation of what the function 1 over e to the z minus 1 looks like. Truth be told, that is a four-dimensional problem because you've got an xy plane linked to another xy plane. So you can ponder that a little bit more and give yourself a headache probably trying to think about it. But I went about calculating the absolute value of 1 over e to the z minus 1 here. This episode, by the way, the algebra, it's pretty thick. There's a lot of it. So I'm not going to list out every step by voice. I'm just going to scroll through. If people have questions, I will be in the comments to answer that. But we're just going ahead and, multiplying the function by its conjugate and taking the square root. Strictly speaking, I believe you're supposed to actually get the imaginary parts in the top here. I didn't do that because I done it on scratch paper once before, and it doesn't really change things. You can multiply the conjugates in the denominator, at least here anyways, in this problem, and it all worked out. You get some trigonometric functions here that cancel out, and then you're left with e to the 2x minus 2e to the x cosine y plus 1 in the denominator. And you go check this out, you will find that this goes to 0 at the origin, and that is that's the pole. So, but to test for a simple pole, what you do is you multiply the function by z, and then you take the limit as z goes to 0. And depending on the value of that limit, it'll tell you whether or not the function has a simple pole. I decided that this would be a good episode to do a review of L'Hopital's rule, which deals with a function that has separable top and bottom components, but they need to behave a special way. The limit of I in the top needs to go to 0 at the same time that j goes to 0, or I needs to go to infinity while j is going to infinity. This is known as an indeterminate form. If that is the case, what you can get away with doing is taking the limit of the derivatives of these two, of the derivative of the top divided by the derivative of the bottom, at that point where you're approaching your limit. So that comes up in this problem quite a bit. And what concerns us right now, at least determining whether or not 1 over e to the z minus 1 has a simple pole, is to take the limit as z approaches 0 and then take these derivatives so that we can solve for the limit. And as you can see here, it does simplify things, and we've got a e to the z in the denominator. Now, the first thing that went through my mind when I started going down this rabbit hole was, are we allowed to use these derivatives? Is L'Hopital's rule appropriate to be used on a complex function? I guess if I was a little more experienced, I would know that for sure, but learning about it now. And it's a very different problem when you're going from real to complex numbers. On the real number line, if you're approaching from the right side and approaching from the left side, it's just one number line that you're coming from on the variable a, when you're approaching the variable a. But if you're doing it in the complex plane, you're approaching from an infinite number of directions in that plane. So, the derivative now depends on two different variables. basically, the way I can sum it up is that L'Hopital's rule, you're okay using it as long as the function is holomorphic on that region of the complex plane. Whether or not it's holomorphic depends mostly on the Cauchy-Riemann relations. You can go ahead and play with these if you want with the function 1 over e to the z minus 1. I'm not sure if the Cauchy-Riemann relations were the only thing. I thought there was one other thing, but consult Wikipedia or your local math or physics department for further info. And if anybody can find holomorphicity in a spell checker, I'll be very surprised. Had some problems with that in the script. So anyways, you'll have to take my word for it that this function is holomorphic, and we can go ahead and use L'Hopital's rule to solve the limit. We get 1 over e to the z after applying those derivatives, and the limit is equal to 1. So a finite value of the limit indicates that we have a simple pole, so that's the good news. If we do this same thing to a arbitrary Laurent series where we just have the variables, no values, we multiply through by z here. What happens is that we find if it has a finite value, then that's only going to happen if all of the coefficients for the higher negative values of z and the principal component, they all have to be equal to 0. These drop off to 0 because they're multiplied by z and various higher powers of z. The only one that should be sticking around after the limit is the coefficient for the principal component, which is b1. So since we know that the limit of z times 1 over e to the z minus 1 is equal to 1, and we know that the limit of of z times an arbitrary Laurent series is equal to b1 for anything with a simple pole, then we have solved for the coefficient of the 1 over z component of the Laurent series, and it's equal to 1. So, and I'd like to reiterate that in this example, 1 over z is the sole principal component of 1 over e to the z minus 1. Hope that made sense. So while the textbook did not list a domain for the Laurent series, I'm going to go ahead and solve this for 0 to 2 pi, in part because there is a discontinuity at 2 pi on the imaginary axes. E to the 2 pi I is equal to 1, and yeah, 1 minus 1 is equal to infinity, so there's a pole there. There's also holes at various other locations on the complex plane. Did make this graph a little bit too small. I am sorry about that. But yeah, you get a pole every at integer values of 2 pi. So, and if you don't know who this is, can't help you there. Anyways, we don't need to worry about them. We're only going to be in this little small section here. Okay, so I started off preparing to do this problem the wrong way. Shouldn't have done that, but that's what happened. So what I'm going to do is I'm going to go briefly through the initial part of this wrong derivation. You'll see in a minute why I'm doing this. It started off by taking e to the z minus 1 and expanding this into a Taylor series for the e to the z portion. We then take the minus 1 on the right-hand side and cut that out, cancel it out. And then we come up with a new summation here, z to the n divided by n factorial. And once we have that, we have z, we pull a z out of the z to the n portion of the summation. And then since it doesn't have any n dependence, we can take it outside of the summation. Bad news, my battery is again starting to die. So this is now going to be a very, very limited version of the episode I wanted to make. I thought I would be able to get away with just recording using a screen capture program. I'm currently at 50%. I started at 73%. So Apple, if you're listening, I hate your battery policies. Okay, so next up, we're really going to gloss over this. The derivation asks you to take this summation and turn it into this. Basically, you're moving the entire summation over by 1. There was no explanation of that, so I did do an explanation here. Basically, we know that we take a variable we call j. We set that equal to n minus 1, and we put that into each and every point on this summation, and it gives us a new way of expressing it. And then you can go ahead and call it basically anything, including Cinnamon, who I drew over here. This is a bear that I once saw eating apples out of a tree. I shot some video of that I was going to put into the episode, and what do you know? No equation, no video editor. So, but the point is, you can name this variable, anything you want, and then you can just turn it back into n. From here, we expanded it, and then pulled 1 out of the summation. Then we came up with this. The idea is that you invert this, and then you invert the other side as well, and then you use a geometric series on this section. Or you use the rules for a geometric series on this section. So you got a 1 divided by 1 plus something, and in theory, you can put a minus sign here, an extra minus sign, and then you get oscillations in the series. You get 1 minus a plus a squared minus a to the third, all that. This is predicated upon the assumption that alpha, the absolute value of alpha, is less than 1. I didn't know it at the time. You can use geometric series for imaginary numbers or complex numbers. But they do need to be within this parameter. The absolute value of the complex number needs to be less than 1. According to Quizlet.com, you can go ahead and turn this into a geometric series. So you end up with you're taking this series and putting it inside of a geometric series. So you have 2 different series, one summed over n, the other one summed over k. And then you go about solving that, and you get your Laurent series. And I do want to add that this will give you the right answer. I ran through it, and it does give you the right answer. And if we bring up Quizlet, you can see here it is a verified answer. And it is for that same domain that I was talking about, 0 to 2 pi. And here's the formulas that they listed out. This is before they invert it, and then after they invert it. Summing up these terms, that was a lot of fun. I spent about a week going ahead and figuring out a way to properly sum them and show how to do it in a lesson. And that was, if nothing else, that was interesting. And I even thought it would be interesting to make an episode just on summing this series over here. But that would be in the context of it being a separate problem, because unfortunately, in spite of the fact that this is a verified response, Quizlet.com is wrong, and they should not be putting this up to as something for people with paid memberships, or even people like me who went ahead and gave them my email address and all, so they could spam me. Yeah, the use of the geometric series is wrong, because the series inside of the geometric series does not meet the parameters. I mentioned the Bohr atom because Niels Bohr himself went ahead and acknowledged that the model, which you probably learned about in an intro quantum mechanics course, is wrong. It has assumptions about classical physics that have no place in a hydrogen atom. But it gave the right data for the hydrogen ground state energy. Such is the case here. This summation does not hold true. It does not hold a value of less than 1 for the domain from absolute values of z up through 2 pi. It actually diverges much before then. If you don't believe me, you can take this summation and plug it into the Wolfram series calculator, and you'll see what happens when you plug in different values of z. It doesn't work. So unfortunately, what you just saw on Quizlet.com and what I've been showing you here is garbage. And that's the reason I backed off on using this in the lesson. By the way, I didn't originally find this answer on Quizlet. I found it on a random blog posting. But after I posted that update video, I did go ahead and find it on Quizlet.com, and I was pretty disappointed that they would be doing this. Strictly speaking, it will work as a summation about z equal to 0 if you keep it within that domain. If you keep it within the for the locations where this does not diverge, which is much more restricted than the domain that they restricted that they showed. So let me be clear. I don't know if hopefully I can. No, I'm not going to try to zoom in on this. But yeah, right here, they're stating that this is valid for the space from absolute value of z from 0 to 2 pi. I want to make that crystal clear. They should not be doing this technique for that domain. But they probably get away with it because it gives the right answer. But if you walk into your class with this on the sheet, I'm assuming your instructor is going to know, and you're going to look pretty silly, so don't do it. Now, derivation, the right way. Oh, already down to 43% of battery, so we're going to have to rush through this. We're going to start off with, what we're going to do is we're going to use the value of the coefficient for the only principal portion, principal component, 1 over z. The fact that we already know that coefficient, it's 1, means we can use that to subtract it off and take limits to calculate the other coefficients. Back when I thought I had more time for this episode, I was going to talk a little bit about Jessie Gender and a podcast she runs. I'm a big fan of her work, and maybe I'll link that in the description. I know this was not supposed to be part of the lesson. It was supposed to be a side note on the lesson. Now I'm running out of time, and I'm trying to figure out how to do two things. But her channel got mercilessly trolled recently on her live streams, and as a side note, I just wanted to say that I love her work, and what was happening wasn't right. And I just wanted to use my platform to say that, even if it is on my last episode. Anyway, So what we're going to do is we're going to subtract off 1 over z, and we're going to take the limit as z approaches 0. If you go through all this mumbo jumbo here, you find that the end result is the next coefficient, a sub 0. So this time we, instead of using Laurent Series components, what we do is we actually put the function in 1 over e to the z minus 1, subtract 1 minus z, and then it's on us to go ahead and calculate out the limit. It ends up using L'Hopital's rule quite a bit. And once we get through all of this, we have negative 1/2 for the a minus, the a naught coefficient. As I said, running out of battery life, so I'm just gonna let you. You're gonna be able to look at the algebra if you want to dial the video back, but I'm not going to be able to stop and explain every step. It's just not going to happen. I already spent quite a bit of time rewriting this. That's why these notes are not as polished as they probably should be. So once we have a sub 0, what we can do is take now 1 over z and negative 1/2 and subtract that off of the function. And here we just do it with an arbitrary Laurent series with a simple pole. And we see that it gives us a sub 1. So in order to calculate a sub 1, we're going to take the limit of z as z approaches 0. Only this time we're not just subtracting off 1 minus z, we're also subtracting off negative 1/2. And then we create a limit here. And I think we already calculated that. I had this in red because we calculated this. This is just, summing up common factors, but I did it a couple of steps back, so I inserted it here. But I forgot to write in a z, so that's why I squeezed it in the bottom here. And I was so disgusted by what I heard about the school system in a certain district in Pennsylvania recently that it sounded like they were making it illegal for history teachers to teach anything about Rosa Parks. Yeah, if you're in the math department in a school that's doing this in Pennsylvania, hopefully, even though they've got the history department under a microscope, see if you can find a way to squeeze Rosa Parks into a math lesson or something, because what's going on with the school district there is just disgusting. There's a number of books that were put on a banned list, and the school district said, we haven't ruled yet, but we are considering the problem, and they've been considering it, so to speak, what seems for like the last 8 months or so. They're just going to sit on that and not teach history, which is, well, it's almost as garbage as Quizlet.com. So, all right, so as I said, the algebra gets pretty weird here. Well, not weird, just there's a lot of it. Got to combine a lot of like terms. I did end up having to scratch out a lot of stuff. This should not be here. These parentheses or these quotations mean the same thing, and the denominator here goes here. So sorry about that. But once again, both top and bottom go to 0. So we take the derivative of this, and then moving on to the next page, taking the derivative once again, combining like terms. There were some 3's here when I accidentally messed up a minus sign earlier. So this is 1, and this is e to the z minus e to the z plus 2 plus e z times e to the z. Moving down a little further, we find again the numerator and denominator both go to 0. So we take the derivative top and bottom, and then combine like terms. Same thing, combine the terms, find out the top and bottom still go to 0, apply L'Hopital's rule. combine like terms, got a 4e to the z and an 8e to the z. And I don't know what was going on here, but scroll down a little further, and you get 1 over 12 for the a sub 1 component of the, a0 component. Actually, forgot which one I was working on. Yes, a sub 1 equal to, so that is the one that you multiply times z. I'm sorry, I think I got a duplicate page here. Oh, you know what I did? I'm sorry. Okay. All right, so we have calculated 1 over 12. We're going to skip 2 pages because they were redos, which I probably should have used for the lesson, but oh well, here we are. All right, so a sub 2, we're now pulling off 1 over z, a naught, and a1 multiplied times z, and we're subtracting all that off of f of z, which will give us a sub 2. Now the algebra starts getting really thick. So you can see just combining a lot of common denominators. We're able to combine some like terms, 24z and negative 12z. And I can see why some people would want to go ahead and use that that explanation that was on Quizlet, because it does look on the surface easier to do, but hard thing and the right thing, once again, look to be one and the same, and that's why we're doing out all these limits. So once again, we find top and bottom go to 0, so we're applying derivatives on the top and bottom. Combining some like terms here. And then applying L'Hopital's rule again, applying derivatives on the top and the bottom. Partway through this, I started getting sick of writing, whether or not something was going top and bottom, and didn't think of a good way to write that, so I just wrote, you get the idea. So applying L'Hopital's rule again. Now it's getting hard to fit all the terms in. Got some like terms here, 144 z e to the z times 72 z e to the z. And then once again this goes to 0, and I'm feeling like I don't have to say it. And derivative top and bottom. Combining like terms. And then we don't really need to worry about a sub 2 because it is equal to 0. So there is no squared component in this Laurent series. And finally, we're going to calculate a sub 3. The purpose of this problem was just to calculate the first 3 portions of the analytic side of the Laurent series. So we're only going up to a sub 3. So I did put in a 0 times c squared just for completeness, but as you can see, it's just going to disappear. And the calculation is similar, though not identical, because now we're dividing by z to the 3. I didn't do that thing where I show what happens when you take the limit of the arbitrary series. It has jumped right into the calculation of a sub 3. So we already calculated a term that looks similar to this as far as combining like terms and all the factors and everything. So I went ahead and kind of copied that from a previous page, put it in here. Now we have a limit with 1 over z squared multiplied times this. We're combining a lot of like terms. I made a mistake and had to scribble something out and put a 6 in over here, but that 6 is correct. This goes to 0 on top and bottom, so we are applying L'Hopital's rule. Combining more like terms. And when I say these go to 0, a lot of times it's a combination of factors of z going to 0, but over here we have a constant 6 and an e to the z. The e to the z goes to 1, then you have 6 minus 6, and that equals 0, so that's justification for using L'Hopital's rule. Applying more derivatives, combining some more like terms in this next step. Had to scratch some things out when I missed a minus sign or missed a term. And once again, top and bottom do go to 0, so we can again use L'Hopital's rule. We're going to take the derivative, top and bottom. And then just really trying to squeeze everything in here. I had this minus 288z component that is part of the denominator, but I had to put it into the next line. These things I scratched out here are the result of missing a term that was supposed to be, I don't know if it was a minus sign or a part that didn't get calculated, but I did scratch it out, and it is minus z squared e to the z in the numerator. And then coming down here, written out much more cleanly, we take the derivative of the top and the derivative of the bottom. And we have this thing, which is getting nice and bloated. And then we have to take the derivative of this whole thing down here. So derivative top and bottom, now using multiple lines in the denominator. Just got to keep track of your terms. It's mostly high school stuff at this point, but there's a lot of it. So we combine like terms going from this line to this line. And then at this point, we are done with L'Hopital's rule. And we just go ahead and insert the values for the limit. I wrote lim over here, shouldn't have done that, but as you can see, 0, 0, 0, 0, 0, 0. So we have basically minus 2 over 1,440. And that all works out to negative 1 divided by 720. And that is the value of a sub 3. And then come down here. We have e to the z minus 1 equal to 1 over z plus a naught plus a sub 1 z plus a sub 2 z squared plus a sub 3 z cubed. And when we insert everything, it's pretty straightforward. This will disappear. And we have the same Laurent series that you saw in not only on Quizlet.com, but in the back of the textbook. So this is kind of a deceptively easy problem insofar as somebody might look in the back of the book, say, oh, I just have to prove that the numbers equal this. But as you can see from what I've just shown you, it's a lot more complicated than that. So until I retake complex analysis, I don't think you're going to be seeing any new problems out of me on this channel, and that could be a very, very long time. There are easier problems I suppose I could throw up on the channel, even a couple of ones I've got solved from a different class that I took. But I just don't feel like doing that, and I don't want to constantly be worrying about when the day is going to come again that I'm going to run out of material to write about. It's too bad. Didn't want it to go this way, but oh well. Till I take another class, this is Pentagram Prime signing off.